Hey folks, today we're going to be talking about Rust and Python and how I think Rust can compete with Python and with a lot of languages that are like Python. So this is partly going to be a Rust introduction for folks who have not played with it yet or have only played with it a little bit. But for the folks who do know Rust already, this is also going to be a bit of storytelling. I want to talk about why I think Rust is as hyped as it is, as hyped as it has been for the last 7 or 8 years. So that's what we're going to talk about. I'm going to record this talk twice. There's going to be a fast version and a slow version, and this is the slow version. So this version is going to be about twice as long. It may be an hour and a half or close to 2 hours, which is too long for most people. But if you don't know much Rust and don't know much Python, but you still want to follow along, this might be the version for you. Some people like the faster version. I will link to that in the description. That's the story we're going to tell today. And we're going to talk about some of the Rust features. You see on the screen here, we have Enums, Destructors, and Aliasing Rules, and how those help us catch a lot of bugs. So I'm excited to talk about these features in particular because I don't usually get to talk about them this way. Usually when I'm introducing Rust, I introduce it by comparing it to C and C++. Right? These are the native languages, right? These are the languages that win the internet benchmarks game, and these are the languages that run on your toaster, right? And the story we usually tell about Rust is comparing it to these. There were good reasons for that. From about 1985 onward, C and C++ had like no competition in this space. It is very exciting that Rust came along and represents new competition. The memory corruption bugs that come up in these languages, right? Rust has interesting new answers for that. That is very exciting. Of course, it makes sense that this is the story we usually tell. This is not the story that I want to tell today. The story that I want to tell today is how Rust compares to these languages, right? These are the managed or garbage collected languages. These are the most popular languages typically. There's a lot of them. Probably everyone listening to this has used at least one of these. And the story for a long time has been that if you don't have to have that speed or that embedded stuff that's running on your toaster, if you don't have to have a native language for those reasons, you're probably picking one of these because these languages just help us get our work done, right? That's how we've thought about these languages for a long time. They just help us get our work done. And choosing C or C++ means, dealing with these extra bugs, right? Memory corruption, dangling pointers stuff. And if you don't have to deal with that to get your work done, then we don't usually pick those languages, right? That's the story for a long time. But Rust has come along, and I think the story with Rust, the relationship between Rust and these managed languages, is in some ways the opposite. So, it's certainly, you pay a learning tax if you have to learn a lot of the concepts that you would learn in C or C++. But instead of having extra bugs for you to deal with that get in the way of getting your work done, you see entire categories of bugs disappear, right? You have way fewer bugs to deal with. And that's, of course, the memory corruption bugs. Rust is famous for that. Those C and C++ bugs that we worry about, those go away, yes. But a lot of bugs that these languages have to deal with every day, a lot of those bugs go away too. So Rust is offering you an interesting trade-off. If you pay that learning tax, you might have less work to do to get your code ready to ship, right? It might make it easier to get your job done, easier to get your work done. It at least makes sense to consider that trade-off. So this is very different from what native languages have represented to us in the past. And I think this is about the other half, maybe the smaller half, of why Rust is as hyped as it is. So that's sort of the story I want to tell today. I want to talk about these big categories of bugs that Rust helps us catch, not the memory corruption stuff, but the bugs that managed languages like Python, like Java, deal with every day. And we'll talk about the features of Rust that help us catch those bugs. So let's dive right into it. The first feature we're going to talk about is enums. Enums help us catch null pointer bugs. So I'm going to throw a lot of Python code on the slide. This is too much code to read. I'm going to fade it out. Don't worry about reading it. We're going to zoom in on it and go piece by piece. This is a little program that I'm going to introduce that uses the none type in Python. That's Python's null or nil, right? So this is just going to be an example for just so we can start talking about null pointers and see how Rust does things. If you don't know Python, or if you just prefer a different managed language, it could be Java, it could be Ruby, right? Feel free to imagine that this program was written in your language of choice, because what we're going to be talking about today, the managed language issues that we're going to be talking about today, show up. The story is pretty much the same in all of those managed languages, right? So if you want to mentally translate this example into JavaScript or Go, feel free. We're going to use Python. I think Python is easy to read. I love Python, so I picked it. Got to pick something. Feel free to translate in your head. Let's look at what this program is doing on the right. So here's some terminal output. I'm calling it scream.py. And what does it do? It screams hello world. Okay, so pretty simple. And then scream.py has one feature, which is that you can give it a file path on the command line. And if you do that, then it instead of printing it to the terminal, it's going to write that string to the file, and we can cat the file and see that it wrote the string. So this is a screaming hello world program with exactly one feature, very small. Let's look at the code. Again, in this slow version, I'm going to try to go line by line to help everybody follow along. If this is too slow for you, feel free to switch to the fast version. So we have this class screaming output, the init method. This is how Python sort of constructs objects. This is kind of like constructors in Python. Self is just the new object being constructed, the new screaming output. And we have this one argument, path. And path equals none. This is the default value, right? And none is Python's null pointer. So this is saying that by default, if you don't supply a path, then it's going to be none. And in the body, we check to see whether it's none. And if the path is not none, we open it, right? And we get a file. So we're going to create this self.file member, this self.file field on the screaming output object. And if we didn't have a path, then we still create it, but the value of self.file is none. Okay. Here's our write method. It's where the screaming happens, right? Just to do something. And the write method has to check, we might have created self.file, we might not have. It might be none. So the write method has to check what mode we're in, ask whether self.file is none or not. If it's not, we use it. If it is none, we write to standard output. That's the terminal, right? Okay, so there's these two modes, and we have to check. And then here's the main code. Not much to see. So we look at the command line arguments. sys.argv is the command line arguments. And if we got one, then we use it. We pass it in, and that's constructing a screaming output from a path. If we didn't get one, then we construct a screaming output without the path. This defaults to none, right? So that's the none case right there. And then we use it. That's it. That's the program. It's not doing much, but it is an opportunity for us to talk about none, about null, how it's used here. And I think everyone here who's used any of those managed languages before has probably seen this stuff before, right? We use null in Java. We use nil in Go. Right? So these are all pretty familiar. And we're all familiar with some of the mistakes we can make. So here I've put a diff on the screen. So imagine I wrote this code instead of this code. This red code is the code that we saw on the previous slide, and the red represents me deleting it and replacing it with this mistaken green code here. So if we forget to check, whether the path is none, and we just try to open it directly, then half the time we're going to crash, right? If the path was none, this is a type error of some kind. You can't open none as a file. It's going to crash. Similarly, right, in the write method here, if we forget to check whether we initialize self.file to a real file, if we just pretend that we always did that and we just blaze ahead and try to write to file without checking, then in the case where file is null, it's a very similar crash. Python calls it a slightly different error type, but it's the same issue. It's like, this is none, and you forgot to check. So again, most of us, right, have used languages that have null. We're very familiar with these mistakes. We probably made a mistake like this in the first 2 or 3 weeks of learning to program, right? These come up every day. And there was a famous computer scientist who called the null pointer the $1 billion mistake. And he called it that because these are just super common, right? We deal with these bugs all the time. And the thing I want to highlight is that, of course, in Python and in most of these managed languages, these are runtime bugs. So we see these crashes when our program is running. If we want to find them, we have to run the program to the point in the code where we made the mistake, right? And that often means writing a lot of tests to try to catch these bugs. Sometimes we don't write enough tests, and we end up finding these bugs in production. So that's why they're called the $1 billion mistake. It's sort of like they're just really common. So let's look at what Rust does instead. Now, again, too much code, so I faded it out. Don't read all the code at once. We can just look on the right. Cargo is the Rust build system. So if the first day you start learning Rust, you start learning how to use Cargo. Cargo run is the simplest way to run any Rust program. -Q is just getting rid of some extra logging here, quiet mode. And just like before, we can pass an argument on the command line. It can print to the terminal, or it can print to this file. And if it prints to the file, we can see it. So this is the same program. It's doing the same thing, but it's written in Rust. And we're about to see how Rust sort of avoids needing null. Rust handles the problems that null is handling, but it handles them in a different way. So we zoom in and we see what Rust is doing differently. We see this enum. So instead of being a class, or what Rust would call a struct, screaming output, in this case, is an enum. Now, folks who know C or Java have probably seen this word. Python has an enum module, right? You can import enum. And in those other languages, it's pretty different, right? In those other languages, enum is just a way to give names to different numerical values. In Rust, it's more interesting than that. So in Rust, we have these different modes that the enum can be in, and that's kind of like the other languages. But here's the big difference, right? So in the file mode, we have this field. We have a field called file, and its type is also file. This is the standard file type from the Rust standard library. So we have a file field, a file member, if we're in the file mode, if we have the file variant. If we are not in the file mode, if our enum is in the standard output mode, we don't have this field. So we have data that comes along with the enums, and we have it sometimes. So it's kind of like null, but working with it is pretty different. So here I've scrolled down to the right method. That's where the screaming happens, right? Just like in Python. And what we see, self here is the screaming output enum. And what we see is the basic way that we use enums in Rust is we match on them. We use the match keyword. It's kind of like a switch statement from other languages. But the way it works here is we name each of the variants the enum can be in, and then we have a block. So within, if the enum that we have, if self is this in the file mode, it's this file variant, then we run this block. And if it's the standard output variant, we run this block. So it's kind of like a switch or an if statement. But the big difference here is in the file variant, we name its field, and then this file field is in scope. So we have file here for this line, right? File is in scope for this block, and it's not in scope for this block. That's the big difference. So we use match to ask what state the enum is in, and depending on the answer, we might have different data. Now, for folks who are seeing enums in Rust for the first time, this is going to be a little too fast, but this is just a quick overview of enums in Rust, because I want to emphasize that we use enums in Rust all over the place. We use custom enums, just like we got here, right? We created a screaming output for ourselves. This is our custom enum, but we also use standard enums that are built into the language. And the first one we see here is option. So this is the new function, sort of like init, sort of. And I've called the argument maybe path here to emphasize that we might have it or we might not. And it is a string, but it's not just a string, it's an option string, a string that might be there or might not. And this is the first place where Python used none, right? But here what we see is that option is another enum. So, right, the first thing we do with it is we match it because it's an enum. So we remember that the screaming output could be file or standard out. The option enum can be some or none. It's the standard option enum. It has those two modes it can be. You might have the thing or you might not have the thing. And if you have the thing, once again, the data comes along in the match, and within this block, but not this part, not this line, within this block, we have the path. And there's some little differences with the parentheses versus the curly braces. I'm not going to worry about that detail, but it's the same idea, right? We've matched on the enum, and we might have this data that was inside of it, or we might not. We have to do different things in the different cases. Very quickly, I want to highlight there's a third enum on the screen here, result. This is how Rust handles errors, right? Operations that might succeed or fail. You might return some successful value, or you might return some sort of error. That is result in Rust, and result is also an enum. So we don't see any matching on result here. We do see constructing some results. So if option was some or none, then the result can be okay or error, ERR, error. We don't see error on the screen here, but we do see okay. So this is constructing results in the success case. And we see this question mark, and I'm not diving too deep into the details, but this question mark is how most error handling is done in Rust, and it is a shortcut. It is syntactic sugar. It is another way of saying match. So this question mark matches on a result enum, like this one, matches on the result returned by file create. If it was an error, it's going to return that error immediately. It's going to short circuit. If it's not an error, it's going to kind of unwrap the successful value that came with it, and we get that here. So I just want to highlight, I understand I'm moving very fast for folks who are seeing it for the first time, but I just want to highlight that we use enums all over the place in Rust. Custom enums, standard enums. It is totally normal to see a function like new here with 3 different types of enums flying around. Right? So this is what Rust does instead of null, basically. And we can talk about making the same mistakes. So here I forgot to match on the path. I just tried to pass it directly to file create. And we see that is an error. So of course, this is the same mistake as we made in Python. But this mistake is coming out of cargo build. I could have used cargo run here because cargo run does a cargo build before it runs. But I wanted to emphasize that this error that we see here is happening in the build. So those of us who've used compiled languages before, whether it's C or C++ or Java or Go, right? We're familiar with compiler errors, right? Those are different from runtime errors. They happen before your program ever starts. And they usually mean that you're not allowed to start your program, which is annoying at first. But it's nice because they're guaranteed to happen, right? If we make this mistake, the compiler is going to check all of our code and we will see all of these errors, even if we did not write any tests. Right? So folks who are familiar with a statically typed language, again, like C or C++ or Java or Go, of course, are familiar with type errors. And this is kind of a type error here, right? We've passed the wrong type into file create. The text of the error message is a little bit harder to follow because we're talking about traits and things. But we've passed the wrong type into file create. But the difference here is that Rust is representing that like optionality or that like nullability, right? Oh, this value could be null. Rust is representing that in the type. Rust is not the only language that does this, but most of those languages that we saw on that managed language slide don't do this, right? Every type can be null for the most part in most of those managed languages, certainly in Java or in Python. And that's not true in Rust. In Rust, values that can be null are a different type. So it makes these errors much easier to catch. This is, again, sort of the Rust version of the same Python mistake we made before. Here's the write method, and we just forgot to match on self, and we just imagined that self had a file field, right? And we just try to use that without checking. And what we see is it itself doesn't have a file field. There is no field of this name, right? The only way to get at the file is by matching. So in general, Rust is going to help you always remember to check what state your enums are in. Now, my favorite thing about enums in Rust is how they help us grow our programs, right? How they help us keep things correct as our programs change over time. So, here's an example where I've got this screaming output enum and I'm adding an extra field to the file variant, to the file mode. So maybe we want to track the path, maybe we want to log it or something. And I'm adding a third mode. Maybe sometimes we want to print to standard output. Sometimes we want to print to standard error, right? When we print to the terminal, there's these two different ways to do it. And the redirect affects standard output by default, but not standard error, right? So sometimes we want to print to standard error. And so I've changed my enum, right? I've added these features, we could say. And as soon as I do that, we look at the build and we're going to see boom, 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 boom. We're going to see all these errors coming out of the compiler. And these are not angry errors or frustrating errors. These are happy errors, right? These are the compiler helping us out and saying like, hey, I see you've added this new field. I see you've added this new mode. Let's go ahead and update all the places in the code where we use this enum. We need to go ahead and update those to handle the changes that you said you want to make, right? We said we want to add a path here. We need to go to this line where we're creating the file screaming output in the new function. We need to put path here in addition to file. We said it should be there. We need to go put it there. It's a compiler error until we put it there. This is the match that was in the write method, and that match was handling the file mode and it was handling the standard output mode, but we've added the standard error mode. So by default, that match is going to need a third arm, right? It's going to need to say what we do in the standard error mode. So by default, Rust is going to require us to update most of the places where we use this enum to match the changes that we said we want to make. So Rust programmers get very used to this. And when we're adding features that involve changes to an enum, we usually do it like this. We usually just change the enum and then build the program and then let the compiler remind us all the places where we need to make a corresponding change. So this ends up being very pleasant to work with, very nice. It's very comfortable. The language is helping you out a lot. And the tools are helping you out a lot. Another way I like to think about what we see here is that we're kind of helping Rust out because we're being very clear about all the states that this object can be in. Right? There's three. We can see that there's three, right? The file, standard out, and now standard error. There's three states. But imagine writing this code in Python or Java or Go, right? So in those languages, we would probably have a file field and we would have a path field, and those fields would be nullable, right? Sometimes they would be there, sometimes they would not be there. Sometimes they'd be none or nil or null. And then for standard output, standard error, we would probably have like a Boolean flag or something. Maybe standard error is true or false. And we could do that. That would work just fine. It would work. But if we did that, we'd have three different fields and they all have two different states, right? File is none or not, or the path is none or not, and the Boolean is true or false. And that's 2 times 2 times 2. That's 8 different possible states for our object to be in. And we only really wanted 3 of them, right? So this enum definition is helping Rust kind of squeeze down that state space from 8 to 3, right? We've been very clear about which of those states we want, which of those states we consider meaningful and useful to our program. And so then Rust can see if we try to construct any other state, that's not what we wanted. But in Python or Java or Go, the other managed languages, it is harder for the tools to know what you wanted because you don't have something like enum that lets you sort of be very clear about that. Now, for completeness, Rust is not the only language with features like this. We certainly see languages like TypeScript, languages like Kotlin, including some sort of like nullable feature in the type system. So they will be clear about types that can be null or not. And that's very nice. And I expect to see that in any new modern language coming out in the future is probably going to do that, right? That's a very nice thing to have. We also have the functional programming languages, languages like Haskell, which some folks may have heard of. Languages like Haskell have done this sort of thing for a long time. They call it algebraic data types, which is a very fancy way of saying it. But so there are other languages that do this. But most of the most popular managed languages do not. And this is one of my favorite things to have when I'm writing Rust. And I often find that when I go from Rust back to another language that doesn't have enums like this is the feature that I miss the most. This helps me catch a lot of bugs. So moving on to the next section. Now we're going to start talking about destructors. So now destructors is the C++ term. So C++ programmers in the audience know exactly what we're going to be talking about. We're going to be talking about cleanup. So Rust calls this drop, right? So the idea is if you have an object that holds some sort of resource, how does it clean up those resources? And when does it clean up those resources? And of course, the first object that we always think of when we think of resources is a file. So I want to launch this section with a question about files. And that question is, do we need to worry? We are opening these files and passing them around for our screaming output. Do we need to worry about closing them? Like, are we managing that resource correctly? And it turns out in Rust, the answer is no, we don't need to worry about it. Yes, we are handling the resources correctly. So I'm looking at the main function from the previous program. This is our first time zooming in on it. And there's not too much to see here, right? We've got the command line arguments. We're creating our screaming output. There's a little bit of fancy type system stuff here. I'm not going to worry about it. We're writing to the screaming output, and then we're returning the successful result of nothing. The sort of the empty tuple is the standard nothing type. And this is the main function. And I want to zoom in on this and think out loud about what's happening to this variable. So this screaming output, if we got a path, the screaming output's going to hold a file on the inside, and we might worry about how that gets cleaned up. And the rule in Rust is that local variables, like output here, this is a local variable for our main function, they get dropped or destroyed or cleaned up at the close curly brace when they go out of scope. So they down right here. So output is going to get dropped right here. And the rule in Rust, very similar to the rule in C++, is that when an object gets dropped, its fields also get dropped. So if we go back up to the screaming output definition, we remember that it has this file field. And the default behavior, we did not have to say anything. When a screaming output gets dropped, if it is in this state where it has a field, that field will also get dropped. And we could pull up the standard library documentation if we wanted to, and we could see that standard FS file says that when it is dropped, it closes itself. Great, that's pretty much the whole story. Files closing themselves. This is kind of the textbook example of resource management. This is why destructors in C++ are very nice and convenient. This is why drop in Rust is very nice and convenient. Now, I want to do a little science experiment here. So bear with me for a minute. I want to kind of check our work here. So instead of just reading the docs or trusting me, I want to see these files being closed. And then that's going to help us kind of ask the same question about Python. So here comes a science experiment. Bear with me. I want to see the files being closed by looking at their file descriptors. Now, this is a term that probably half the audience has not heard before. What is a file descriptor? A file descriptor it's a number, usually a small number. And when we open a file, what we're really doing is we're asking the operating system to open that file for us, right? And the operating system is going to do some stuff, and then it's going to hand us back a little number, a little handle to that file. And kind of in the Unix, Linux world, we usually call that a file descriptor. So it's sort of like a pointer, but it's not pointing into memory. It's just a number that we use when we're talking back to the operating system, writing to the file, or closing the file. We use that number to refer to it. It's the handle that the operating system has given us. Okay, so usually these are under the covers and we don't have to look at them or think about them, but it is interesting to look at them and think about them in this case. So what am I doing? I have a little program and it's just printing 3 lines of numbers. Okay. And we see that I'm calling my function 3 times. So I guess that's why I have 3 lines. What is the function doing? Okay, it's going to print something. So there's the line. But what did it do? We opened a file, file 1. We opened another file, file 2. It does not really matter what this path is. This is the sort of like always empty file path on Unix, right? Doesn't matter what file we open. And then we print the raw file descriptors from each of those 2 files. So we're sort of looking on the inside and seeing that number that the operating system gave us to refer to the open file handle. Not exactly the file path. It refers to the open thing, the handle that we have to the file. Okay, so we're just looking on the inside, looking under the covers. And what we see, 3, 4, 3, 4, 3, 4, and the specific numbers don't matter. But what is interesting about this is that we see the same numbers every time. Okay, so the first time we opened file 1 and file 2, we got these descriptors. The second time we got the same descriptors. And the third time we got the same descriptors again. So what that is telling us is that file 1 and file 2 got closed in between here and here. And they got closed again in between here and here. So if file 1 and file 2 were still open, then the descriptors that they were using on the inside, those would still be taken. Those would still be reserved. We would still need those to refer to the open files. And so opening 2 more files would need 2 different descriptors, and we would see the operating system giving us different numbers. So if file 1 and file 2 were staying open, we would see 3, 4, 5, 6, 7, 8, or something like that, right? We don't see that. And so that's telling us that we are closing these files. And so that's just sort of, this is a science experiment. This is evidence that the story we told on the previous slide is true. So when these local variables go out of scope at the closed curly brace, at the end of every time we call this function, they get dropped. And dropping under the covers closes those files. And the operating system understands that when we've closed them, those file descriptors are freed or released, and it will reuse them. Okay, so that was a little science experiment. I don't know if I'll call it a fun science experiment, but it was a science experiment. Thank you for bearing with me. So now, of course, what's our next question? Our next question is, what happens in Python? Do the files get closed in Python? And the answer, for better or worse, is it is complicated. So this code is doing the same thing. We now know exactly what this is doing, and Python calls it the file number instead of the raw file descriptor. Same thing. And we see the standard Python interpreter, what we might call C Python if we look on GitHub at what that project is called, behaves in the same way. Okay, but there's these other Pythons that behave differently. So Python per se does not guarantee what it's going to do, and different Pythons do different things. So some folks who are following along might know that Python, the standard Python interpreter, uses what we call reference counting. That's its strategy for cleaning up objects. And reference counting will free these files, will clean them up at the end of the function. In this case, it's kind of like what happens in Rust. But here's another Python interpreter called PyPy. It's not as common as the standard one, but many companies use this. It's faster in some cases. That's why some companies use it. And we see that PyPy is not closing the files. PyPy does not use reference counting. PyPy uses a more standard garbage collector. I think it's mark and sweep, one of those garbage collector buzzwords. PyPy does that. So these files will be closed later at some point, but they're not closed quickly. And so the next time we get to the same function, the third time we get to the same function, those first 2 files, those second 2 files, they're still open. We see the same thing with MicroPython. So if you run Python on like an Arduino, like these tiny little microcontrollers or your toaster or whatever, MicroPython is the version of Python that you're using. And MicroPython also has a sort of standard garbage collector, mark and sweep kind of thing. It's not doing reference counting. So you see the same behavior. Okay, so the story is a little bit complicated. Since 99% of the time when we use Python, we're using this one, it might be tempting to rely on this behavior, but we should not rely on that behavior. And I want to do one more slide of trivia, one more little science experiment. I'm going to make this example a little more complicated. I've added some very silly lines that are just creating some maps, and I'm not going to worry too much about the details, but we see what happened here. So let me go back and forth a couple times. So I go back and forth and back and forth, and you can see the numbers on the right changing. Right. So if we do this thing, whatever I did, then all of a sudden we see Python behaving differently. So the standard Python interpreter uses reference counting, and that often cleans things up immediately. But if we create something called a reference cycle, a sort of circular graph of references, then the reference counts will not go to 0. And if you have heard of this concept before, you may be interested to read these lines of code, maybe pause the video and think carefully about how this creates a reference cycle, what the reference counts are at the end of this function. If you have not heard of a reference cycle before, don't worry about it. This is a little bit trivia. And the important thing is that in Python, just like in Java, just like in Ruby, just like in Go, right, in basically all of the managed languages, we have to remember that resources do not necessarily get cleaned up quickly. And so this is why every experienced Python programmer, every experienced Java programmer, right, experienced programmers in all these languages will always tell you that we need to explicitly close resources like files and sockets and things like that, right? These resources that we have a limited number of, right? On my machine, I think the limit by default is like 1,000. I can have 1,000 files open. And that's like a medium-sized number. It's not tiny, but it's not huge. And if my program is running for a long time and opening a lot of files, and if I'm leaking those files and not closing them quickly, I can run into trouble. I can run up against that limit. And that's why experienced programmers will tell us we always need to close our files. So let's look at what that looks like in Python. So going back to the Python code, I've added a couple sections here. This is the sort of bare minimum attempt to clean up the resources. So we've defined the close method. Once again, we do have to check whether we have the file. It's important not to forget this if statement. But we've written this correctly, and we can call close at the end. Now, to be clear, this is a tiny little program, and this program is about to exit. And when it exits, all the files get closed and the operating system cleans up everything. So in this tiny example, do we really care about resource cleanup? No. But this is a teaching example, and we should imagine that maybe some similar code could be in a larger program that runs for a long time, and that larger program might care about these issues, right? So this is just an example, and we want to think about like, okay, how do we do this correctly in this tiny example? And this tiny example is a little bit incorrect. So we will close the file in the happy path, right, if everything goes well. But if not everything goes well, we could see the write method raise an exception, right? That's how errors are represented in Python. And if the disk is full or the write fails for some other reason, right, we raise an exception here. And if we raise an exception here, we never run this line, right? The exception kind of unrolls the call stack in our program. And if that crashes the program, then again, maybe we don't care about cleanup because we're going to crash. But if there's a higher level loop that's catching exceptions, then we might have bailed out on this line and never gotten to this line. And then in that error case, if that exception is caught, we've leaked the file for some amount of time, right? Until the garbage collector runs and figures out that it's been, it's time to free that file. Now, again, in this case, the standard Python interpreter might do reference counting and might free it quickly, but we don't want to rely on that. So how do we write this code correctly to free resources correctly in every case? Here's the most straightforward way. We use try finally. So this is what Python calls it. I think these keywords are probably familiar to most programmers in any managed language. The idea is any exception thrown in here. On its way out, we will still run this cleanup code in here, right? So I think programmers in most languages have seen something like this and know what this does. So this is the first version of this Python script that is really correctly managing resources and cleaning up resources in all cases, including the error case. Okay. So folks with a year or two of Python are certainly not seeing anything new here. Some of you might wonder whether we could use the with keyword here. I'm not going to talk about that just yet. What I want to do is I want to make this example just a little bit more complicated. Make this program just a bit more complicated to make the resource management a bit more complicated and see how that feels in managed languages like Python. So what are we changing? Too much code to read, as always. Don't read all the code unless you feel like it. But we can see on the right what we've done. So I've replaced scream with scream many. Okay. And this is what we've done. So now we support multiple files on the command line. And if we do this, then we've written to all of those files and we can see the output in all those places. Okay. So before we had 0 or 1 file, and now we have potentially many files. So let's look at the code. Here's the main code. So I've given us this helper open outputs. We're going to look at that in a second. You can see it above. But for now, I just want to know that open outputs returns this list of screaming outputs. Okay, we get a list here, and we loop over it, right? That's the for loop in Python, pretty similar to any language, and the for loop in the cleanup side, right? A separate for loop for cleanup in the finally case. This is a small change from what we saw before. Nothing big here. The cleanup is 3 lines of code, which is a little bit annoying. We might not get that right every time. But what I really want to look at is this helper. Right? I want to look at open outputs because what open outputs is doing is very simple. Right? The happy path is 4 lines of code. Right? We create the list. We loop over all the paths that we got in the argument. For each of those paths, we open it and we put that screaming output that we got into the list. We return the list, right? Super simple helper function. We write helper functions like this all the time. But the cleanup code, the error handling code, is 5 lines, right? Got this try, and we have this 3-line except block. And of course, the reason we have to do all this is that we can't use try finally here, right? We don't want the cleanup to happen in the happy path. If this function succeeds and we've opened all the screaming outputs and we're going to return them, well, of course, we don't want to clean them up, right? The caller, the main code, is going to use them, right? If we close them now, that's broken. So we don't want to do that. So we only want to close them in the error case. So we have an except here. Again, try except. Most languages have something like this. Some languages call it try catch, right? Any language with exceptions does something like this. So only in the error case do we get here. We have that cleanup loop, and then we have to remember to re-raise the error, because we don't want to swallow the error. We don't want to forget that the error happened. We just want to do the correct cleanup on the way out. So again, folks with a year or 2 of Python experience are not seeing anything new here. Of course, I'm not saying that this is brain surgery or whatever, but it is a little bit annoying that this very basic function, there's a big difference between the lazy way of writing this function and the correct way. There are a lot of little pitfalls, right? We could forget to do cleanup at all. We could forget to re-raise the exception. There's just a lot of pitfalls here. And when our programs have a couple dozen little helper functions like this, what are the odds that all of them handle resource cleanup correctly in all the error cases? Those odds are probably not great, and we sometimes accidentally end up relying on the garbage collector to clean up our resources for us. That's sort of the way it is, right? In most managed languages, and it doesn't usually bite us. But as our programs get larger and more complicated and run longer and have lots of modes, we start to run into these resource edge cases, right? Running out of file descriptors, things like that. So that's the story in most managed languages. What does this code look like in Rust? Too much to read, but same idea on the right. Multiple file paths, right? We're writing that output into 3 different files. Same story as the Python we just saw. Let's look at open outputs. What do we see? Where's the cleanup code? And where's the error handling? Well, the error handling is here. That's the error handling. There is no cleanup code. So this is the naive, lazy way to write this function in Rust. This is the way I wrote it the first time without thinking about it. And this function correctly handles cleanup in the happy path and the error case by default. This is 100% correct. So in the error case, we hit this question mark. We see that we failed to open the file inside of here. Then we're going to return that error. Right? The result will be an error. And then our local variable outputs, same story as before, is going to get cleaned up. It's going to get dropped, the closed curly brace. Anything we've pushed into that vec already, maybe some of the file succeeded before we returned, those are going to be in there. When the vec is dropped, it's going to drop those elements. They'll clean themselves up. It's all automatic. And it happens immediately. It doesn't happen later. But then here's the interesting part. In the happy path, in the success case, we return outputs. And that's what this is what that looks like in Rust. When we return outputs, here's a little buzzword. Rust is going to call that a move. This is move semantics. And if you haven't seen that in Rust before, or if you haven't heard that term, we're not going to get into the nitty-gritty details, but we can just say, okay, Rust sees that we're moving outputs to the caller. We're giving those resources away. So in this case, when we've returned outputs, Rust knows that outputs should not be dropped at the close curly, and the cleanup doesn't happen. The move of outputs prevents the destructor from running. So the C++ folks who are following along, the story is kind of similar. It feels similar to use the code. The details are very different, but the story is kind of similar. When we move out a return value, it doesn't get destroyed. So the defaults in Rust just do the right thing here. It is very difficult to write this function in a way that fails to handle resource cleanup in either case, the happy path or the error case. Now, I understand that not everybody is as excited as I am about closing files. I think reliably closing files automatically is super cool. I love how it feels when I write code like this. Not everybody is as excited as me. And these edge cases that we're talking about, to be honest, they're pretty rare, right? Unless we have a big complicated application, we might never see any of the problems that Python code might have had if it wasn't 100% correct. But what I think is more exciting is how these same features, this destructor-based cleanup, this drop cleanup, how that helps us out when we're dealing with multi-threading and when we're dealing with locks. We're locking mutexes, and we have to remember to unlock those locks, and that's kind of like cleaning up a resource, kind of. And the same features end up being very helpful. And when we do have multi-threaded code in any language, we definitely run into locking bugs all the time. Those are very common. And so Rust's help here is very valuable and I think very exciting. So I want to introduce an example of some multi-threaded code, and I'm going to throw a lot at you. So bear with me. First, I want to show you a small function that is definitely not multi-threaded. There's no threading here. There's no locks here. But I just want to get this function in our heads so that we have the structure, and then we'll see the multi-threaded version. That's how I want to do this. So bear with me for just a minute. So add 1 to smallest. Okay, that's what this little function is doing. And its argument is a list of integers. I32 is the 32-bit signed integer in Rust. And this little syntax here is a slice. And if you haven't seen that before, don't worry too much about it. It's a list, right? It's a list of 32-bit ints. That's what the ints variable is. We start at index 0 right here. We call that the smallest index. Of course, it's the smallest index we've seen so far. We're just starting at index 0. And we're going to look at all these ints, and we're going to try to find the smallest one. So we loop over all the other indexes from 1 to the end of the list. And at each position in the list, we compare the next integer we see to the smallest one we've seen so far. And if the next integer is less, right, if this condition is true, then we update smallest index to refer to that new position that is the new smallest integer we've seen so far. So by the end of the for loop, smallest index refers to the index of the minimum value in the list, or one of the minimum values, right, if they're equal. And then we have that, and we use it, and in this case, we do whatever we want with it. In this case, we add 1. So I said I was going to add 1 to smallest, so I find the smallest, and I add 1 to it. Okay. So, there's some Rust syntax here that we might not have seen, but I think everybody who does programming has written some loop like this at some point in some language, right? We're going to loop over a list, find the minimum value, do something, right? So I think this loop is pretty familiar. So let's juice it up. Let's see what this code looks like in a multi-threaded program. So here's add 1 to smallest, the same function. But what we see is we've got a bunch of mutex stuff around now. Now, to be clear, I'm not creating any threads here. I'm not doing a thread spawn. We'll do something a little bit like that later. But what I'm doing here is I'm using data that other threads might also be using. Right? So I'm imagining that there could be other threads in this program, and this data could be shared with them. And so instead of a list of ints, I have a list of mutex of int. Right? So mutex is a lock, right? Mutual exclusion. And the mutex in Rust contains the data that's locking. So I have a list of locks, and each lock contains an int. So these are locked ints that might be shared with other threads. We might be using those locks to coordinate with other threads. Okay. Basic structure is the same. I start with smallest at index 0. I loop over the other indexes. I do a comparison. I update my smallest variable if the condition was true, and I add 1 at the end. So we've seen that basic structure. We already know what it's doing. How is it doing it? The lock function, the lock method on the mutex. I'm gonna ignore unwrap here. There's some error handling. I'm not worried about it. I'm just looking at lock. Lock returns a mutex guard, basically. Okay. And the C++ people know what a mutex guard is. A mutex guard has 2 jobs in Rust. And the first job is very familiar to the C++ people. So when we lock the lock, we get the guard. And then this guard is going to go out of scope at the close curly brace, right? This is a local variable. It goes out of scope. And when it goes out of scope and it's dropped and it's cleaned up, the guard's job, its first job, is to unlock the mutex that it came from. So locking gives us the guard, cleaning up the guard unlocks, right? That's pretty nice. It means that we can't forget to unlock the mutex. That's automatic. It also means that the unlocking happens correctly in error cases. That's very nice. And again, same story with C++, right? So the guard in Rust now, this is different from C++, has a second job. So we see here that we are using the guards to stand in for the integers that they protect. So this star operator, if you're familiar with C or C++ or Golang, then you've seen this star before. This is the dereference operator. So these guards are acting like pointers or references, and we're kind of reaching through them to get at the integers that are behind them. If you have not seen this before, I'm just going to say don't worry about it. You can kind of squint at it and mostly forget that the stars are there. And we just imagine that the guards are standing in for the integers inside the mutex that they lock. Okay, so the code looks the same. So why, I guess it's nice that the unlocking is automatic and that the code looks the same. But I want to ask more specifically, why am I putting this example on the slide? I want to ask, where do these mutex guards get dropped? Where does the cleanup happen? Because if we look closely, it's actually very interesting. So half the story we already mentioned, smallest guard, whatever mutex guard is ultimately there, is going to get dropped here at the end of the function. Fair enough. So the last unlock of whatever that smallest mutex is, that's going to happen at the end. Okay. The other half of the story is what happens to next guard. So by default, next guard would go out of scope here. So every time through the loop, at the end of the loop body, we would drop next guard and we would unlock that mutex. That's the default behavior. But what we see here is that sometimes we do something different. So sometimes we do this assignment of next to smallest. And if we do that, it's kind of like the outputs example in the previous slide where returning it by value moves it. It's the same story here. Assigning next to smallest by value moves next into smallest. And that does 2 things. The first thing it does, again, like the previous example, it means, oh, this was moved away. If we move this away, then it doesn't go out of scope. It doesn't get dropped at the closed curly brace where it would normally get dropped. It got moved, so wherever it got moved to, we'll drop it later. And we know where it got moved to. It got moved here. So this does not get dropped if it gets moved. And then the other half of what's happening here is there was a value here before, right? So smallest guard had a previous value, might have been the one at index 0, or it might have been another one that we got from the loop. And so if we're going to move next into smallest, we have to drop what's already there before we do that move, right? So we do cleanup of the previous value of smallest guard, and then we move next into smallest. That is totally automatic. And we don't usually have to think about it, but it's interesting to think about it here because what we see is that we always unlock one mutex, some mutex, at the end of each time through this loop. But which variable, which guard we clean up, which mutex we unlock, depends on which code path we take. If we if this condition is true, if we take this path, we execute this line, then the guard that we clean up is smallest guard, the previous value of smallest guard. If this condition is false and we don't execute this line, we get to the end of the loop, and the guard that we clean up is next guard. So we're always unlocking one. It just depends on what we did in the code and where the moves happened. And on the one hand, I think this is like really cool. It's like super subtle. So this function only ever has one or two mutexes locked at any given time. It's cleaning up as it goes. It's always unlocking the ones that it's done with. That's like really nice. It's really compact. Writing the same code in Python or Go would be quite noisy. We see that sort of like the open outputs helper function, we definitely cannot use something like try finally here, or the Python with keyword, the Java try with resources keyword, the C# using keyword, right? Golang's defer keyword. None of these cleanup mechanisms are appropriate here because we don't want to always clean up next guard at the end of its scope, and we don't want to always clean them all up at the end of the function. We want to clean them up as we go, and the scope is a little bit dynamic. So this is super cool, but on the other hand, it's also a little scary. Like when we write multi-threaded code, we tend to get pretty worried about bugs, and if this locking and unlocking stuff is so subtle and so invisible, should we be worried about this? That's sort of my other thought here. And the very best thing about all this code is not just that it's convenient, right? It's not just that the code is small and compact and clean. It's that if we make mistakes, Rust is going to catch them. It is very hard to make mistakes with what we're locking and unlocking in this code. Well, there are still some mistakes we could make. If we say greater than instead of less than, then our logic is wrong. We're going to get the wrong answer. But if we make a locking mistake, like here, what I've done is I've just flipped the assignment. Like I fell asleep and I just wrote this backwards for no reason. And now my code doesn't make sense. And I'm trying to move from smallest guard into next guard. And so smallest guard is going to get like emptied out multiple times. Like, am I unlocking smallest guard like many times? What does that even mean? And the answer is it doesn't mean anything. It's completely invalid. And Rust sees that it's invalid. And Rust won't even compile this code. So this is what happens with most of the small mistakes we could make with mutexes in this kind of system just result in compiler errors. And the compiler errors are not trivially easy to understand. Like we have to know what Rust's rules are for moving things. And so it may not be totally clear that the way to fix this is to swap them back. I mean, the compiler might not be able to tell you that. But the compiler is at least going to catch the bug, right? So when we do crazy things, the compiler is going to catch this. And if our crazy thing is that we dropped the guard too soon or we never acquired the guard at all, Rust is definitely not going to let us get away with that. We're not going to see that bug at runtime. Here's another example. This is a little heavy on the syntax. So if you haven't seen mutable references in Rust before, you can kind of squint at it. But what we see here, the main thing to focus on here is that instead of holding on to a mutex guard, I'm trying to hold on to this thing that's inside of it. So I'm taking a reference or a pointer directly to the integer on the inside of the guard. So like this part of the expression is the guard, but then I'm doing this other stuff to it. It's some syntax here. But this is getting the reference to the inside. So my variable is not holding on to the guard. So this is a big category of interesting mistakes we could try to make. So we could try to take a guard and get something from it, but fail to hold on to the guard as long as we've held on to the things on the inside of it. And we see that that's actually what happens here. So if we've held on to just this reference, then when we assign next to smallest, we're only assigning the reference. So that this mistake, this change means that we're not moving a guard here. And that's very subtle. This is maybe exactly the kind of subtle mistake we might have been worried about, right? Like, oh, geez, it's completely invisible that this, on this line at least, that this is moving a reference and not moving a guard. So, would we really catch this? Would we notice mistakes like this? Maybe not. It's hard to notice mistakes like this, but the compiler sees it. The compiler sees it. The compiler knows that the reference that we got, this guy here, the value of next guard, I'm still calling it guard because this represents a mistake, right? The value here came from this temporary mutex guard here. Rust sees that at least in some cases, we are trying to use that value after the temporary is gone. We didn't preserve it. That is a lifetime mistake. It doesn't compile. So this is the part of the compiler that we often call the borrow checker. The borrow checker is the thing that's supposed to be catching all those bugs from C and C++, right? So when we're comparing Rust to managed languages like Python and Java and Go and Ruby, we're not usually thinking about the borrow checker because the garbage collector is supposed to take care of that stuff. But, well, when it comes to resource cleanup, we remember we didn't want to rely on the garbage collector because the garbage collector does its work later, and we need resource cleanup to happen sooner, immediately when we're done with resources. So we're not relying on the garbage collector. So we're in this space where we're doing things manually, and it might be very easy to make mistakes where we've cleaned up an object, but we still have like references to that object somewhere, and we're still trying to use it. Maybe the file's been closed and we're still trying to use the file. I think a lot of us have seen that error before. And we see those bugs from time to time. But if a language like Python tried to do this very aggressive, very automatic, very invisible cleanup that we see in Rust, we would get a lot more of those bugs, right? This cleanup happening automatically makes it a lot easier to hold on to a reference to something that has been cleaned up. And so I think what we're seeing here is that borrow checker, yeah, it's usually about the C and C++ bugs, but it's also about helping us deal with this really aggressive cleanup. That's interesting. And again, in managed languages, with resources where we have to do things by hand, we care about that, and that's nice to have. And so Rust is able to make these very, very aggressive trade-offs because instead of paying for this convenience with more bugs, we pay for it with a learning tax. We have to learn how to write code that the borrow checker accepts. We have to learn how to live with the borrow checker. That is a learning tax. But once we've paid that tax and we're writing Rust, we get the advantage of this really clean and automatic resource cleanup, this really hard to screw up sort of way of doing things. And we don't have to pay a bug tax. We don't have to worry about more mistakes creeping into our code at runtime. That's a very nice trade-off. Now, of course, like we said, C++ does do automatic cleanup, similar to what Rust is doing here. And C++, I think, pays for that with a bug tax, right? So Rust is this interesting kind of third way of doing things. And I think that's a theme that's going to keep coming back. All right. Moving on to our last big section. Spooky action at a distance. What do I mean by that? How do aliasing rules help us catch that? We have all written this book, right? So anyone who's used really any language, any language in the managed languages or C or C++ has written this bug. What have I done? Right? We have a person has favorite foods. Okay. And everybody likes donuts. So we start with a list of donuts, and I create Alice with that list of donuts, and I append apples to Alice's list of favorite foods. So Alice likes donuts and apples. Bob also likes donuts because everyone likes donuts. And so I append bananas to Bob's favorite list. So I expect to see that Alice likes apples and Bob likes bananas, and everybody likes donuts. But what I actually see is that everybody likes apples and bananas, right? What? Like what? Like if you're not sure why this happened, feel free to pause this video and see if you can spot it. I'm going to highlight it now. And of course, many of us have done this many times and seen this mistake before. This is the mistake, right? So we passed donuts in both places. So instead of having Alice's list and Bob's list, there's actually only one list, and Alice and Bob are both referring to it. And so when we did these appends, we were appending to that one list. And when we did these prints, we were printing that one list twice. So again, this comes up in most languages, and most of us know how to fix bugs like this, right? We need to copy the list. So now this is maybe the most common way of doing it in Python. The list function copies a list. You can also do it with the indexing, slicing syntax. You can use the square brackets here. I do it this way, and then now we get the correct answer, right? So now Alice's list and Bob's list are two different lists. And maybe the second copy was optional. We could have used donuts here, but this first copy fixed the bug. Okay. So a subtle point I want to make here. Of course, you have to remember to do this. The other thing to keep in mind is that this does fix this case, this relatively simple case. But if we were dealing with a more complicated data structure, for example, maybe we have a list of lists or a list of dictionaries, this fix here, it only copies the outermost list. So if there are mutable objects on the inside, we could still get a version of this bug, even though we tried to fix it, if the shared objects on the inside get changed. Right? So this is what we call a shallow copy. It's only copying one layer. In a more complicated case, we would need a deep copy of sort of everything all the way down. That is a little bit annoying to deal with. It gets a little bit complicated in many languages. In this case, strings in Python are immutable. We don't have to worry about it. This does fix this case. That's just a subtle thing to keep in mind. How does Rust fix this? I'm going to skip through the Rust code real quick because I just want to clarify that the fix is the same. It's exactly the same idea. We're copying the list. In this case, donuts is a vector. It's just sort of how Rust says list. And we clone it. So we get a copy, and then we fix the code. And that's fine. To that subtle point from before, this clone, if we had a list of lists, right? If this was a vec of vecs, if it was a vec of hash maps or something like that, this clone would be a deep copy in those cases. And that is quite nice when we're in those more complicated cases. It's not a shallow copy. But in this case, we don't have to care about that. This is the fix. The more important difference, the fix is pretty much the same. The important difference is that the bug, the bad code, didn't compile in Rust. So when we tried to write this mistake, we tried to make the same mistakes in Python, the compiler caught it. We didn't have to run our code. We didn't have to get to the print to see the mistake. The compiler is going to say, hey, where you use donuts here, just like with outputs, just like with the mutex guards, right? This is a move. You've moved donuts into favorite foods. And so if you try to do it again, well, you can't move the same object twice. We've moved this away. We didn't put anything back there. So this is a compiler error. You just can't write this code. So Rust is helping us catch this bug. Rust is going to catch this bug immediately. It's not the kind of thing that can sit around for a long time before we notice it. Now, there are other ways we could try to make the same mistake in Rust. So this moving, we call that moving by value. There are other ways to use objects. We don't have to use them by value. We can take references to them. And if we do that, here's an example. So this version is trying to do pretty much exactly what Python was doing, right? So we had this one list and we're taking references to it. So this code is trying to have both people refer to the same list. These are called shared references in Rust. The idea is that they share the same object. You can have more than one of them pointing to the same object. And this is actually perfectly legal. You can do this in Rust. You can create the people like this. But if you do this, then what's going to happen is when we get to the next line, this is illegal. So the rule in Rust is when we have these shared references, we can't use those in most cases to mutate things. We can't make changes to the shared object, kind of for exactly the reason we're talking about, right? It's shared, and if you're making changes from one place that are going to appear through the other place, that's pretty confusing and can cause a wide variety of bugs. We just can't do this. These lines don't compile. You are not allowed to call push to modify a vec through a shared reference to that vec. It just doesn't work. Now, of course, sometimes we do want to take references to things and modify things through those references. We can do that. In Rust, that's called a mutable reference. It looks like this. And if we try to do it this way, we see that the compiler still catches the mistake. So this is legal, and this by itself would be legal. But the rule with mutable references is they're sort of the opposite of shared references. It's like, yes, you can use them to do mutation, but you cannot share them. So when you have a mutable reference to an object, that has to be the only reference, shared or mutable, to that object while the reference exists. It cannot be aliased in any way. There cannot be any sharing while you're doing mutation through a reference. And so what we see here is it's kind of like the first example with moving, right? It's sort of like we tried to move donuts twice. It's a different rule, but it's solving similar problems. We cannot take a second mutable reference to donuts while the first one is still alive. We know the first one is still alive because it's held inside of Alice, and we're still using Alice down here. So the first one's definitely still alive at this point. The compiler sees that we cannot make a second mutable reference to the same object. So, part of the learning tax of learning Rust is there are a lot of different things you can do. There's 3 ways to try to make this mistake, and we have to learn about all of the rules that apply in all these cases just so that we can get our work done. But the takeaway I want to highlight here is that in all these different ways of trying to make the same mistake, the compiler catches all of them. None of these mistakes get through the compiler. Let's see a few more examples of this kind of thing. So we still have, in this case, we still have people, they still have favorite foods. We've added a method, add favorites. It takes another person and we loop over all the other person's favorites and we append them to ours. So this is sort of like copying the other person's favorites and adding those favorites to our list. Okay, fair enough. Sort of a monkey see, monkey do with favorite foods. And then what do? I make a terrible mistake, right? I create Alice, that's fine, Alice likes apples, but then I call add favorites with Alice on Alice. Now this is a weird thing to do. It's kind of odd that I would try to do this, probably a mistake. What does it do? The answer is it loops forever. This becomes an infinite loop, and inside this loop, it's continuously appending apples onto the same list. So this list of apples keeps growing and growing and growing until it uses all the memory on my machine, which takes several seconds. And then my mouse stops working and my whole machine locks up. And then eventually, this was on Linux, eventually Linux kills the Python program, circular.py, right? So this is like some sort of circular reference. The fundamental issue here, of course, is that self and other person are both Alice. So as we loop over other person.favorite foods, we are changing that list. This is the sort of mistake that many languages call iterator invalidation, right? So this for thing, this syntax obtains an iterator that knows how to go through this list of favorite foods. But if the list is changing, then we have to ask complicated questions about what it means to keep using an iterator as the list it's referring to is changing. And we don't want to be asking those questions. It turns out in Python, if I made favorite foods a list, but if I'd made favorite foods a dictionary, like a map, this loop would crash immediately. Python does not allow you to loop over a map while you're inserting and deleting things in that map. But for better or worse, it does allow you to do that to a list. And that, I think many of us who've used Python for a few years have accidentally written infinite loops of this kind. In Rust, this just doesn't compile. And it doesn't compile for the same reason we saw before. Code is very similar. But this line violates the mutable aliasing rule, right? We see that we're taking a shared reference to Alice. That's what's going to be the other person. But this dot here, the method call, also implicitly takes a mutable reference to self. This is a method that mutates the person. So it takes a mutable reference to self, and self is Alice. And Rust can clearly see that that means you're taking a mutable reference to Alice while at the same time you're taking a shared reference to Alice. That's not allowed. Right? Violates the mutable aliasing rule. This just doesn't compile. So you can write code like this in Rust and just never have to worry about what happens if self and other are the same person. They just can't be. That's actually quite nice. That's quite nice. A lot of very complicated C++ bugs to do with like collections and lists and copy constructors and things come from forgetting that self or this can be the same as the other, right-hand side. There's a large category of bugs that come from forgetting that these two things can be the same. In Rust, they cannot be the same. That's actually quite nice. Another sort of related issue, what am I doing here? I have a list of functions, and I'm looping from 0 to 9, and I'm appending these anonymous functions, these lambdas. This is what other languages call a closure. or something like that. So this is a function that takes no arguments and it prints I. And I might have imagined that each of these functions would print a different value of I, right? I'm creating them when I takes all these different values. But by the time I get to this loop, they're all referring to the same value of I, which is the last value of I, and they all print 9. I think this is I don't know how common this bug is, but I think this is a bug that most people have seen in any language that has anonymous functions like this, functions that capture their environment, right? So you can't do anything like this in C, but you can do this in C++. This function captures its environment, and it's capturing it in this case by reference, and that variable in the environment is changing, and this behavior is counterintuitive. If you know Golang, Golang version 1.22 came out earlier this year, and they actually changed the meaning of for loops in the language. So this is how long? This is 14 years after Golang 1.0 came out. They changed the spec definition of for loops to fix this bug, because this is a very common bug. They changed the language itself, but most of the other managed languages and C++ still do this. In Rust, this doesn't compile. Right? That's our theme, right? Rust is just catching this entire category of bugs at compile time. This doesn't compile. In this case, we see does not live long enough, so that's a borrow checker error. Rust sees this variable I kind of going away at the close curly brace every time. We could also imagine that I was behaving like Python, where it sticks around and it's just getting mutated. And in that case, instead of being a lifetime error, this would be a mutable aliasing error, right? If this was a mutable variable that was changing, it would not be okay to make many different closures that all refer through shared references to that changing value. Right. So either way, this code is not going to compile. It turns out that it's a lifetime error. Now, if you want to make this work in Rust, you need to learn this keyword. It's the move keyword. This keyword causes this closure, and this is sort of like the parentheses of the closure. It causes this closure to copy the value I. So this corrects the code, and each closure gets its own copy. And that's probably what we wanted. The move keyword is not obvious. I think its name is slightly confusing in this case. So this is just another learning tax. So you have to learn this keyword and what it does. It's a learning tax that we pay in Rust. So it's not obvious how to fix this. The first time you try to do this, it might be a little confusing how to get it working. But again, the takeaway is the same. It's when it wasn't working, we get a compiler error. We don't get confusing behavior at runtime. So we have to work through these compiler errors. We have to learn the rules, but everything's up front. Everything's clear. And once the code is running, we know it's correct. That's not always the case. There are many bugs we can write. We can flip the less than and greater than signs as much as we want. But from the perspective of these aliasing bugs, these spooky action at a distance bugs, if the code is running, it's correct. So once again, like in the last section, I think the most exciting application of this feature, this borrow checker, these rules, right? These rules that are a learning tax, but are also helping us catch bugs. The most exciting application is multi-threading, right? Threading has a lot of scary bugs, right? Threading is famously difficult, and Rust is going to help us deal with that. So I've written a tiny little program here that's going to add up all the numbers from 0 to 99, and that's the correct answer, okay? And instead of using a regular for loop, I'm using a for each. So this looks kind of like Ruby or maybe Scala, languages that like to use iterators and combinator methods like this. And it takes a closure in the body, and this I is going to be each of these numbers, and we add them all to sum. So it looks a little different, but we can see that it's doing the same thing. I wrote it like this because writing it like this makes it very easy to multi-thread the code in Rust. So we can pull in a library called Rayon, and we only had to change this one line. We added this extra special magic method from the Rayon library. It's called into parallel iterator. So it's taking this regular range of integers and it's turning it into some sort of magic Rayon thing. And now when we loop over all those integers for each, Rayon is going to have a thread pool, and it's going to throw that work into the pool, and we might have lots of different threads all doing our little closure all at the same time. And of course, this is a silly example because 100 is not a lot of work, but we could imagine this is doing more work. The important thing is not that this example is silly. The important thing is that this example is wrong. This example is broken. It's broken because sum plus equals I, this is a shared variable. And this closure, this body of the loop, is trying to mutate that variable. And that's perfectly fine. I'm going to go back. That's perfectly fine here. We can mutate that variable in the loop, just like we can mutate a variable in a regular for loop. There's nothing wrong with that. But doing it from multiple threads, that's a mistake, because now we have that famous threading bug. I call it the ATM problem, right? 2 ATMs, read my bank balance, add 100 to the number they read, and then write the new balance. But they're stomping on each other, right? The second write writes the same value as the first write, and we thought we were adding 200, but we only added 100 because they raced against each other, these 2 ATMs, right? It's the same issue here. You're going to get the wrong answer if you run code like this, and it's actually even worse than that. In the native languages like C and C++ and Rust, this is actually undefined behavior. The memory model says you must never do this, and the compiler can do very weird things if you ever do this. So this is very bad. And so we should be very happy that Rust catches this at compile time. So we're not going to get into the nitty-gritty details of the closure traits in Rust and how exactly Rust sees this problem. But the short version is Rust can see that this closure is being shared by many threads, and that means that it can't do mutation of the outside world in its body. Rust can see that. There's a few different steps, but it sees that. It doesn't let us write this. Now, what we can do is write multi-threaded code like this if we use locks correctly. So I'll throw this code on the screen. It's kind of a lot because I know that maybe most of the people watching this don't have practice using mutexes, right? So we saw these methods before when we were talking about add one to smallest, right? So we've seen this, but we don't have a lot of practice with it maybe. So I'm not going to worry too much about the details. The point is I've thrown the mutex in all the right places. The code is still doing the same thing. Here's the read write, and here's just reading it at the end to check the value. And this code is now correct because the mutex is going to make sure that all these threads have to actually wait for each other. When they're touching this value, none of the ATMs can run at the same time, right? And of course, that makes this all very silly because there's no point in multi-threading if all the threads are going to do is wait on the same lock. But this is an example. And the really, really nice thing about this example is that Rust catches the mistakes. It lets us write the code when we've used mutexes correctly, and it catches the mistakes when we don't. That is very, very nice. People in the Rust world call this fearless multi-threading. And this is very different from our experience multi-threading in most other languages, including all the managed languages, including Python. Right? This sort of automatic stuff where if it compiles, you know you did the locking correctly. This is very nice. So I said I was going to talk about functional languages eventually, and this is where I want to make that comparison. So there is this other category of languages that were famous for a long time for catching these same bugs, right? It's functional programming languages. Haskell, OCaml, Scala, Scheme, Lisp, right? A lot of us learned one of these in school. If you studied programming in school, I did Scheme in school. I certainly have not done any of it since then. But and these functional languages, for the most part, they don't do mutation. Some of them, like Haskell, are very aggressive and very pure about that, and the others the story is a little bit more complicated, but they don't encourage mutation. They don't do very much mutation. And by avoiding mutation, they avoid this entire category of bugs that we were just talking about, right? If I'm sharing a list, but that list will never change, then I never need to care that I'm sharing it, right? If my closures are all sharing a local variable, but that local variable never changes, no problem. So they solve the same category of bugs, but they do it with a very big hammer, right? No mutation is a very big hammer, right? In most normal programs that we write when we're trying to get our work done, we do a lot of mutation. And learning how to do without that is a very big learning tax. We have to get very comfortable with recursion in these languages, right? We don't have normal loops. We have recursion. It's a whole different style of programming. And it is very interesting to study. And for a long time, right, there was this feature of these languages, the correctness, right, catching all these bugs was and is a very big feature at this very high cost. So these languages never caught on. They were never quite as popular as the managed languages, or even as C and C++. I think because of that learning tax and because of that performance tax that you pay when it's much harder to write the normal programs that we write that do mutation. So I think the other way I like to tell this half of Rust's story is that Rust is about solving those same problems, right? It's about catching all the same bugs that the functional languages have been famous for catching for so long. But it's a third way, right? It's a different way of doing it. Rust still lets you do mutation. It lets you do aliasing. It just doesn't let you do them at the same time. You have to pick one, right? You can alias values, you can share them, or you can mutate them, not at the same time, right? So it's a much smaller hammer, or it's like two hammers, and you get to choose at any given time which hammer you're using, right? It's a middle ground. It is a very interesting third option in this space, and it catches all the same bugs, right? And so this I think is the other half of why Rust is so hyped. It's like, yes, the big half is like it can do native language things, and that's great. But the other half is it can do all the things we're used to doing in normal programming languages, and it can help us catch all these bugs that help us get our work done, and we don't have to make big sacrifices to use it. The big sacrifice that we have to make to use it is we have to learn it, and it's hard to learn. But it can do the things that we're used to doing in Python, in Java, in Go, right? And it can do them while catching all these bugs. So that's very, very exciting. I think that's the other half of why Rust gets as much hype as it gets, is that people who learn it, many of us learned it to do native code stuff, right? We learned it to write super fast code or embedded code or whatever. But once we learn it, we see, oh, wow, this actually has something to offer in almost any program. That's very interesting. It's very exciting. I want to close with some little bonus slides here. Of course, one of the things that Python in particular is very famous for is standalone scripts, right? So here's an example. What does this script do? It's a little screaming echo, right? So I give it echo.py hello world, and it screams it back at me. And I support the -n flag from the standard echo command that gets rid of the new line, right? So, yeah, we write little standalone scripts, little utility programs like this in Python all the time. Here's the standard argparse module that helps me define those command line arguments, right? And I parse the arguments, and I print the command line arguments, and maybe I print the new line. Tiny little program. So those of us who use Python write tiny little programs like this all the time, and even in projects that are written in other languages, whether it's Java or C++, we see these little utility scripts all over the place. They're very useful, right? Python is great at this kind of thing. And so this little bonus slide that I want to leave you with is you can do things like this in Rust. It's kind of funny. You can play with it. So here's the same little program written in Rust using the clap library, the command line argument parser library, to do the same thing. And you can play with this today. It requires this little third-party project called Rust Script. You have to install that. So it's not standard. And it has this very noisy syntax at the top where if you've seen the cargo.toml syntax, when you create a cargo project, it has a cargo.toml file. And part of it looks like this, and this is where the dependencies go. So Rust Script has this like very noisy kind of way of putting part of cargo.toml in here. You can do this. If you run echo.rs, it will build itself the first time, which sometimes takes a while, right? Clap takes several seconds to build. And then it'll cache that, so it'll be fast after that. So that's interesting. You can play with this. I would not do this in production today. Rust Script is not standard. It's hard to do things like specify what Rust edition you want to use, right? All the features of cargo.toml are not there. You can play with it. But, closing thought, there is a nightly feature. Rust has an accepted RFC, sort of like a future change, where cargo is going to support this kind of thing officially itself. It will officially become possible to put cargo in here. So I'll go back, right at the same place we put Python, in a Python script to run it like this in the command line, we can put cargo in there. Not today. You have to use nightly cargo to do this today, and there's a bunch more noise here. But you can play with it today, and you get the whole cargo.toml syntax here at the top. So it's just like having a standard Rust project, but it all fits in one file. And when this eventually lands, I don't know if it'll be this year or next year. Sometimes things take longer. I'm hoping by next year. When this lands, it'll be supported by cargo. It'll be supported by Rust format. It'll be supported by Rust Analyzer. Right? All the tools will know how to understand this. And you'll have the option of writing these standalone scripts in Rust. And I'm not saying I would always do it this way. There are some downsides here. I think a lot more people know how to read your Python code than know how to read Rust. And the first time you run it, you have to wait for it to build. You also, if you're fetching dependencies, you might need to talk to the network the first time you run it. So there are reasons why I might not reach for this for every little script, but there's a huge benefit here, which is once you're doing things this way, you can add dependencies, right? You can pull in whatever dependencies you want. You can grow this list as large as you want, and it all just works. And on the Python side of things, those of us who have more Python experience and have dealt with pip, the Python package manager, and virtual environments, right, and taking dependencies in Python, it is quite painful to take dependencies in Python. If you're coming from a one file kind of situation with no dependencies, just the standard library, and you're trying to grow that tool a little bit, take some dependencies, maybe you don't like the standard argument parser, maybe you want to use a custom one, that moment in the life cycle of a little Python script is very painful. Taking your first dependencies in Python requires some restructuring, or it requires callers to call you in a different way. That's true of many languages. And so I think the sort of temptation that Rust will offer, the reason that Rust will be an interesting option in this space is if you write a little script in Rust, you can grow that script as far as you want, and you never have to change your workflow, and the callers never need to know what dependencies you took. It just works. So I think Rust's strategy for a long time in the C and C++ world has been to kind of sneak its way in, take small steps into existing projects, not by telling them to rewrite the whole thing in Rust. Some people do say that, but those people are annoying. It's not commonly by rewriting a giant C++ project that you introduce Rust. Often what you do is you rewrite a little tiny module, a little library, and Rust and C++ can talk to each other. And it's not easy to do that, but it's doable. And that's one of the ways that Rust has been growing. I think this will be a way that we see Rust growing in the future. So calling Rust from Python is a little bit harder than calling C++ from Python. Calling Rust from C++. I don't expect to see a lot of Python modules getting rewritten in Rust in common applications, but it is interesting that these little scripts, right? When you have a little script, maybe you wrote it in Python at first, the script is growing, it's doing more, it needs some dependencies. You don't want to change the way all the callers call the script. Rewriting little scripts like this in Rust when they've grown just big enough to need some interesting dependencies, that is an interesting option. I think that might be a way that we see Rust kind of working its way in little by little to a lot of the places where in the past we've used Python or Bash, right, or other scripting languages. So little bonus ideas here. Watch this space. Again, this is not standard yet, but it will be in the future, and I'm looking forward to that. So this, like all the slides we looked at before, is another reason not to write everything in Rust necessarily, but another reason why we can consider Rust. Rust is a viable option, an interesting option in just about any project. And I think that's a big part of why Rust is as hyped as it is, why people are as excited about it as they are. So I hope that story was interesting or useful to you. Thank you for listening.